Hi guys, Mr. John here. If my voice sounds different, well, that's because I feel kinda crappy right now, but I promised to make a video, so here it is. Please excuse the mumbling that you are about to hear. This is the same buck converter that I showed you in the previous video about a little circuit in the base of a small incandescent lamp. It's a very simple buck converter, constant current buck LED driver that you can build using just 2 transistors and a couple of passives. Really simple. As you can see, it doesn't have many parts. 2 transistors, 1 ceramic cap in the feedback, 10 ohm resistor there as a sense resistor, capacitor on the input to provide low impedance voltage source to the circuit. Every circuit really likes it, to be honest. It's an input decoupling capacitor. It's a good rule of thumb to add it. The inductor, of course, because you want some element to store the energy. The freewheeling diode, your load, 1 watt LED, and the ammeter showing the current through it. It's not the proper way of doing it, actually, because my meter is not a true RMS meter, and so I cannot really trust the measurement on the DC range, because the current through the LED is not a straight line, it's a ripple. But the funny thing is that there is apparently some RC filter inside this meter, and it does the job reasonably well, averaging that ripple, so the current that you will see is reasonably close to a truth. So I'm gonna apply 10 volts now. You see the LED glowing. The current is about 126 milliamps, 126, while the input is about 70 or 60 at 10 volts. Now, let me show you what I was talking about in terms of a ripple current through the LED. I'm gonna go insert 1 ohm resistor in series with the LED, and you will see that ripple current on the screen of the scope. Okay, the 1 ohm resistor is installed in series with the LED. Let's stare at the scope. Circuit is on. And that's what we have across that resistor. That resistor is 1 ohm, so the reading in millivolts we see here, we can transfer it to milliamps. You can see that that ripple is about 3 divisions peak to peak. The setting is 20 millivolts per division, so it's 60 millivolts peak to peak. And since a 1 ohm resistor is used, that's 60 milliamps of ripple current through that LED. The sweep of on the scope is half a microsecond. You can use this data to see what the frequency of this converter is. I'm gonna align it. Stupid probe. I'm gonna align it for you. Here. See, it's about 5 divisions. Oh, 4 divisions, excuse me. 4 divisions at half a microsecond. 2 microseconds, which count for yourself. So that's why you can't really trust the reading of this meter. However, as I mentioned, it averages that triangle wave good enough, so the reading makes sense. Not a great idea, but still. The schematic now. Schematic is really simple. If it straight away resembles a linear current sink to you, well, that's because it is a linear current sink with few external components to it, namely this diode, choke and the capacitor. If you remove this diode, this capacitor and this choke, connect the LED straight to the collector, you will have a linear current sink, and that will work just fine. But the whole purpose of a switching converter is to have a bigger efficiency. It's a linear circuit, so it dissipates all the unnecessary power on the switching excuse me, on the main transistor. And by adding an inductor there, you introduce storage element to the circuit, because when this transistor switches on and off, you will want the current to keep flowing through the LED even though when this transistor is off. So that's why you have inductor there. Inductor is a pesky device. The waveform you saw is a triangle, right? So right now the switch is just turns on and the inductor resists the change, so the current rises slowly. Here the transistor switches off and the inductor now changed its mind. It's a very pesky device. Now it wants the current to keep flowing, so the current taper just ramps down slowly again. And this portion is flowing through the through your freewheeling diode, while this portion is flowing through the transistor. Okay, now I ain't gonna go into very deep explanation. First of all, I'm not the best at explanations to start with, and I really feel crappy right now, so yeah. The value you see here, that's some measurements I did using 3 1-watt LEDs in series as a load driven at 300 milliamps, and I had this input voltage and I calculated this efficiency, which is not too bad, as you can see, 84%, not too bad at all. 3 1-watt LEDs were about 3.2 volts per piece at that current, so that's 3.2 times 3, which is 9.6 volts. So the input was 12.6, output was 9.6 LED, 3 volts of difference, and the efficiency was 84%. Now let's calculate the efficiency of a linear current sink in that kind of application. That's your output power, 9.6 volts across LEDs times the current through LEDs. Oh, excuse me, we should really put over here, divide by input voltage 12.6 by the current. Since it's a switch, it is a linear converter, the input and output current is gonna be very close enough for this little calculation. 76%. Not a huge increase, but it makes much more sense when you have larger output to input differentials, namely 21 volts input, we have 77% efficiency. And if you're gonna go and just replace 12.6 with 21 volts, we now see that the efficiency of the linear circuit will drop to 46% roughly, while this thing still rocks 77%. Not great, but still better, much better than the 45% here, 46. You can improve the efficiency by replacing the BGT with a MOSFET. However, if you do that here, I tried it and it doesn't work right. You need to rearrange some stuff. Anyway, I'm gonna quit it here because I'm just gonna fall asleep right now. Thanks for watching. See you.